Before we do an energy calculation on the Bohr atom or the hydrogen atom, I wanted to take a quick look at some equations for different types of energy. So kinetic energy is defined as 1/2 mv squared, where v is the velocity, so anything moving has kinetic energy. Potential energy often is written as mass times the acceleration of gravity, or height. It can also be a potential energy between things that have charges, electrons and protons. Work is a form of energy, so if you've had physics, you know that work is defined as a force in newtons times the distance in meters. So a newton meter is a joule, so we'll be working in SI units, so we'll see our energy values given in joules. Pressure times a change in volume is also an energy unit. So if we recall the ideal gas law, PV equals nRT. P times V, pressure times volume, does give us an energy unit as well. And there's energy between two charges separated by a distance. Electrostatic energy, your electric bill, we really can write energy in terms of the power definition. Power is energy divided by time. So if we take power and multiply it by time, we can get back to energy. So a kilowatt hour, for example, might be what your electric bill is. And anything that is above 0 degrees Kelvin, which everything is, has kT energy. K ends up being the universal gas constant divided by Avogadro's number. So K, lowercase k, is capital R divided by Avogadro's number. So that's really an energy per, it's probably a capital A. But that's not really necessary for us to know. E, the type of energy for electromagnetic radiation or light, that's the part of the focus of this chapter that we're looking at. So the energy of electromagnetic radiation or light is always the frequency multiplied by Planck's constant, so we will take a look at that. In an earlier chapter, we talked about heat as one form of energy. So heat is often abbreviated by Q, and if heat's exchanged at a constant pressure, then we can call QH. So we can talk about delta E is the same as delta Q or the same as delta H. It's often in chemistry, there is no expansion work, so energy is often approximated by the heat component. These are quantized energy states that occur within a molecule, so bonds can vibrate, rotate, or translate, so we don't care about those. This is Einstein's famous equation, E equals mc squared. So what we're going to do is we're going to be talking about electromagnetic radiation or light, and that is the type of energy that's given off when an electron moves within an atom. So let me see if this will come in focus. This is a picture, so most chemistry books have something similar to this. This is the Bohr atom, so we see that right here. And that always means we're looking at hydrogen. So the H in this spectrum is for the atom hydrogen. So N equals 1, 2, 3, 4, 5, and 6. We've talked about that earlier. That is the principal quantum number, or the energy shell, where the electrons are. It's also the rows on the periodic table. So as we look at this picture, I like this one because it shows us the lines that we see for hydrogen. It shows us the corresponding electron transitions for that. So the red line is when the electron falls from energy level 3 down to energy level 2. That's a small energy difference, and so we have long. When that occurs, that will give off energy and release a red photon. And if we wanted the electron to jump from n equals 2 up to n equals 3, we would just have to add that same amount, or that same wavelength of light. So the wavelength of light is always a positive number, the sign on the energy term will just tell us if the electron's increasing in energy by going up or giving off energy, decreasing by traveling to a lower energy level. So the lowest wavelength, or the shortest wavelength transition that we can see, is when the electron falls from the n equals 6 level down to the n equals 2 level. So we're going to be using an empirical equation to actually calculate the energies for these transitions. And once we have that, the energy calculated, then we will calculate the wavelength of the light associated with that. So this really was kind of the beginning of quantum mechanics, was understanding these very discrete lines that always appear. And Niels Bohr is credited as for his role in atomic theory. So what we're going to do is calculate, let me get this in focus now, delta E, there we go, calculations for the Bohr atom. And again, that automatically means we're talking about hydrogen atom. Hydrogen's only got one electron, so it's the easiest one to deal with. And we're going to look at this empirical formula, which empirical just means it's not really based on theory, but somebody had the patience to work at something until they got the correct answer. I don't know why this fades in and out. I'm going to not have it autofocus anymore. I'm going to adjust the focus myself, and then it should stay. Okay. So that equation looks like this. Delta E, and this means per photon. So this photon means one electron making a transition. So that is equal to this constant, negative 2.18 times 10 to the minus 18th, and that's a joule, an energy unit. And then we're going to multiply that by 1 over n squared final. So that's where the electron ends up, and that n is the energy level n, minus 1 over n squared initial. And again, this works beautifully for hydrogen. So if we calculate that, calculate the energy released when an electron falls from n equals 3 to n equals 2. So it starts at n equals 3 and it ends up at n equals 2. So we would call that the electron transition, or electronic transition. Okay. So we're just going to plug 3 into the initial n value, so we'll have to put a 3 here and square it, and then the electron's final state was the n equals 2, so we'll put a 2 here and square it. So in the TI calculator, I'm going to use the double E key, so that EE key means times 10 raised to the power of, so I'll enter that as 2.18, hit the double E key, negative 18, and then we can just put the parenthesis there. 1 divided by final is 2 squared. So we could square that in our head or just hit the x squared button. Minus 1 divided by 3 and square that. And I don't know if that will show up that well. Let me scoot that up. So we would just plug that in. And so negative 2.18. And then the double E key is below the comma. It's kind of hard to see. So we hit the second EE. That means that it knows that that's one number, EE, negative 18, so we don't have to hit the times 10. And then put the parentheses, 1 divided by 2 squared, 2, and hit the x squared button, minus 1 divided by 3, square that, close the parentheses, and if we do that, we get this very small number, negative 3.03, we'll call it. So delta E equals negative 3.03 times 10 to the minus 19th joules. So it's a very small number, but that's because there's only one electron making that transition. And so the energy of that light would be this value. The negative sign means energy, or we could say light, or we could say a photon is released or given off. So the sign tells us if the electron's going uphill in energy, or in this case, downhill in energy. It's losing energy. Now, once we have the energy calculated, we could use a couple of other fundamental equations that we saw earlier. So this is a very fundamental equation for radiant energy, where H is Planck's constant. So 6.626 times 10 to the minus 34, a very small number. And that has units of a joule times a second. So if we know the energy, we could calculate the frequency. And I don't think we're going to stop and do that, but, well, maybe we will. So if I divide both sides by H, then the frequency is the energy divided by Planck's constant. So I suppose we can do that. We're going to take the absolute value of that energy because the sign just tells us if energy is given off or absorbed. So we'll use the absolute value of that, 3.03 times 10 to the minus 30. Oh, I'm looking at the wrong thing. Times 10 to the minus 19th joules. And if we divide this by Planck's constant, 6.626. Here's where we definitely want to make sure we either use parentheses in the denominator or the EE key so that we do not have a order of operations problem when we enter this. Our joules are both going to cancel, and so our unit here will be a 1 over a second. Of course, 1 over second sometimes is written as s to the minus 1, or given the guy's name, Mr. Hertz, that did a lot of work with that. So this number is already in the calculator. So I'm just going to leave that there, and I'm going to divide that by Planck's constant, and I'm going to ignore the negative sign. So I'm going to divide that by 6.626 and use the double E key. And there's two E's here, but that's because the alphabet is also on this calculator. So the two E's is just going to show up here as one E, negative 34, and enter that. And now we're going to ignore the negative sign because frequencies aren't negative. And we'll write this as 4.6 times 10 to the 14th. And then that unit would be a per second unit. So frequencies are huge. And that is how many times that wave oscillates back and forth per second. So once we have the energy, we could calculate the frequency. And then once we have the frequency, we could calculate the wavelength using another very fundamental equation. And that is the wavelength of light times the frequency of light always multiplies together to give us the speed of light. So the speed of light, I'm going to round that to 3.0 times 10 to the 8th meters per second. And if I wanted to do a substitution, I could solve this equation for frequency. So frequency would be dividing both sides by wavelength. Frequency would be the speed of light divided by wavelength. So we can relate energy directly to wavelength using this substitution. So instead of writing frequency here, if I write frequency in terms of the speed of light and wavelength, I can rewrite this equation as E is equal to h, Planck's constant, times frequency, but frequency is the speed of light divided by wavelength. So these two equations fundamentally are the same thing. We're just substituting for that value. And normally, once we have the energy of a transition, we want to calculate the wavelength. So I'm going to rearrange this equation and write wavelength is equal to h times c divided by the energy. Or we would get the same answer if we plugged this value for frequency into this equation and solved for the wavelength. So either way will work, but it's most common to know the energy and to calculate the wavelength. So let's do that. H is Planck's constant, so I gave that to us up here. 6.626 times 10 to the negative 34. A joule times a second will be our unit. And then we'll multiply that by 3 times 10 to the 8th meters per second. And when we do that, the second units are going to cancel. And then we'll divide that by the energy value that we calculated right up here. Again, we're going to use the absolute value of the energy, so I should make that distinction right here. Lengths are never going to be negative. The sign of the energy term just tells us if the system is losing energy or gaining energy. So we'll ignore that negative sign, and we'll put EE negative 19 joules down here. So again, we're using the absolute value of the energy. Our joule units are going to cancel. So when we do this calculation, our wavelength will be in terms of meters. So if we just do this really quick, 6.626 EE negative 34 times 3 EE 8. Oh, I messed up. EE negative 34 times 3 EE 8, and then divide that by 3.03 EE negative 19. So I hope that, yeah, that's right. So we'll get all that plugged in. Planck's constant times the speed of light divided by the energy that we just calculated, and we get 6.56 times 10 to the minus 7th, and that is meters. 6.56 times 10 to the minus 7th meters. If we would like to compare that to data that is in the book we just looked at, if we convert a meter to a nanometer, one big meter is 10 to the 9th little tiny nanometers. So if we multiply this by 10 to the 9th times EE9, so if we multiply that answer by 10 to the 9th, we'll get 656 nanometers, which does fall in the visible part of the spectrum. In fact, this is that orange-red line. And that is the line that we saw when we looked at the textbook. Bring this back, and so the line that corresponds to the 3 to 2 transition we see right here at 656 nanometers. The transitions that fall to the first energy level are going to end up being in the ultraviolet part of the region. So the only transitions we're able to see, because our eyes only see the visible part of the spectrum, are these 4 transitions: 6 to 2, 5 to 2, 4 to 2, and 3 to 2. If we calculated this transition, the 3 to 4, that transition has too low of an energy to show up in the visible part of the spectrum. So that would fall in the infrared part of the spectrum. So there's the only transitions we can see are those that occur where our eyes pick up, and that's between about 400 and 700 nanometers.